All right, ladies and gentlemen, welcome back for another round. This is Mr. Doolin. I thank you so much for tuning in. Today what we're going to do is we're going to take a look at metallic bonds. So metallic bonds occur when metals release their valence electrons into a mobile, free-flowing pool of electrons, and this pool of electrons is often referred to as a sea of electrons. And so one of the hardest things for students to wrap their heads around is that if you even just touch a leg on your chair, which is metal, that's a metallic bond, right? And even though it feels solid, the thing to consider and keep in the front of your mind is that the electrons there are actually mobile. So what I want to do before we move on is I want to actually review covalent bonding and ionic bonding really quickly. So covalent bonds, they're this electrostatic attraction of a nucleus to an adjacent atom's valence electrons, right? So what we see there is that we do not get a transfer of electrons, so sharing of electrons occurs, and this is because the electronegativity values are pretty similar to each other, and we would say that the change or the difference in electronegativity values is something less than 1.67, right? The opposite of a covalent bond would be an ionic bond. And so an ionic bond, we have a very highly electronegative element, and it's going to remove valence electrons from a very low electronegative element, relatively, right? And we're going to get the formation of positive ions, which are cations, and negative ions, which are anions, and this occurs whenever our electronegativity values are generally higher than 1.67. So these are the two types of bonds that we've talked to this point, and now what we need to do is we need to delve into exactly what are metallic bonds. So the largest difference between a covalent bond, ionic bond, and a metallic bond is that with metallic bonds, there's not really a bond as in the traditional sense of covalent and ionic. And what we see here is that the metals actually just release their valence electrons into a general pool of mobile electrons. So there's not necessarily a bond in the traditional sense. This mobile pool of electrons is often referred to as the sea of electrons. It's very important for you to understand that those electrons are mobile and that what we're left with is this positive cores that have general non-directional attraction to all the electrons that are surrounding it. The other thing to make sure that you understand is that their metals are not releasing all their electrons. It's just the valence electrons that get released into this sea of electrons. And so the diagram that I've got down at the bottom of the page here actually represents the sea of electron model. And so what you see here is that we've got our positive cores. They're drawn in black here. And then we see the general release of electrons. So these little green dots here represent the electrons. And notice there's no literal organization of those electrons. And again, that relates back to the fact that they are free-flowing, that they are mobile. They're allowed to move and they can move around. The other thing to understand is the sense of non-directional bonding for my positive cores, and it's the idea that this positive core here in the center would be attracted to all these electrons around it. And then the same thing for this positive core over here, it would be attracted to generally all of the electrons around it. And so there's not one sense of direction for that particular attraction, as it's attracted in all directions to, again, that free-flowing mobile sea of electrons. And so what we do is we end up with two different properties of my metals that are known as conductivity and workability. And so we'll approach conductivity first. So conductivity actually comes in two different forms here. We'll say thermal conductivity, which is the ability to conduct heat. And then there's also electrical conductivity, which is again just the ability to transfer electrons from one place to another. Now the conductivity, either thermal or electric, is based upon these free-flowing mobile electrons, right? Because electrical conductivity, since the electrons are already free to move, they can move from one place to another with very little energy input. The thermoelectric conductivity, again, goes back to the idea of what thermal energy is and what it's going to transfer, right? It's going to be represented in the form of kinetic energy as that temperature increases, and guess what? Kinetic energy is actually increased. Right? Again, it's the electrons. Since they already have that ability to move freely, it's relatively easy, again, for us to increase their kinetic energy, and so that gives us and rises to that ability for thermal conductivity. All right, so now what we're going to do is we're going to address the workability of our metals, and the workability, we're directly going to address the malleability and ductility of metals. Now, malleability is the ability to actually beat a piece of metal out into a flat sheet. So if I had a cube of metal, I can could actually literally just hammer it and put some physical force in there and beat it out into a flat sheet. Ductility is the ability to take that same chunk of metal and actually pull it out into a wire. And so what we see here with workability is the workability is due only in part to the ability of those positive cores to be pushed around. Since they do not have directional bonding, again, let's go ahead and take a look at this positive core up here in the top right hand corner of the drawing, and I can actually take this and with force I can push it anywhere I want to push it, right? Because it's still going to be surrounded by electrons, it'll still be attracted to those electrons, but with workability and because these positive cores are in that mobile sea of electrons, I literally with force can push them around in between each other. So it's the ability of those positive cores to be pushed around that leads to the workability of our metals. And then the last thing that we're going to address before we leave is because different metals release different numbers of valence electrons. And so what we'll see is that the number of electrons actually leads to differences in properties. And so the example I have here is a sodium +1 versus a calcium +2. Well, in a metallic bond, sodium only has 1 valence electrons to release. Calcium has 2. And so the electron pool for our calcium metals is actually larger. And so what we see is that can lead to differences in workability and also conductivity between calcium and sodium. And so what we may see here is, right, again, because sodium has a lower attraction to the sea of electrons, just because there's fewer electrons released, it may be a more workable or a softer metal, right? Whereas calcium we would predict, because now I've got a larger positive core to push through a more abundant sea of electrons, it might be a little bit harder relative to sodium to be able to work that. The other opposite part of that is conductivity, and that would be a little bit opposite here, because I'd expect calcium probably to be a better conductor of electricity than I would expect sodium to be, right? Because again, the conductivity is based on the number of valence electrons that are in that sea of electrons, and calcium has a larger sea of electrons than sodium. So when you're looking at differences between metals, be sure you're taking a look at, hey, what's the charge of that positive core, and how does that affect, right, in terms of workability or number of electrons released, the different properties of the metal. Well, all right, ladies and gentlemen, that's all. If you have any questions, I'll see you in tutorial for those. Otherwise, I will see you in class.